Well, so first I'd like to thank Jameer for organizing this really nice workshop. So I think there's a lot of people in the audience that aren't maybe necessarily from the field of quantum optics primarily. So I thought I'd spend a lot of this talk just kind of giving a gentle introduction to even what the problem that I'm interested in is. And also just kind of throw out a lot of questions I have about this problem, which might kind of, in the hope that maybe it connects with something that, many body physicists and so on might know something about. Okay, so the general motivation is that these days we have a lot of exciting experiments in AMO worlds that can interface atoms and light in a quantum coherent fashion, and we can do a lot of things with it. So this ranges from creating quantum memories for light to generating photon-photon gates, quantum metrology, exploring many-body physics with photons, and so on. And these are all kind of real experiments. And maybe a kind of general theme in the field is that these days experimentally we can do a lot. But honestly, it'd be nice if the experiments also worked a lot better. And to try and capture a little bit what's the challenge in making experiments work a lot better. Fundamentally, a single atom and a single photon, which you can consider to be the building block of atom-light interfaces, they kind of intrinsically just interact very inefficiently. So maybe one way to characterize that is if you were to take a single atom and bring it up to electronic excited state, it's going to eventually drop down to the ground state and emit a photon. That photon is going to go into 4 pi in a kind of dipole radiation pattern. But in optics, we don't know how to catch 4 pi radiation. What we can do instead is catch kind of relatively simple modes, like a kind of Gaussian beam with some beam area A. And the problem is that the overlap between a Gaussian beam that we can know how to generate and catch and this kind of dipole 4 pi radiation pattern is relatively small. So it's on the order of the wavelength squared divided by the beam area. And for this kind of equation to make sense, one has to kind of obey the diffraction limit. So you can't just focus a beam arbitrarily tightly either. And so when you put in the kind of real coefficients and kind of real experimental considerations, if you were to try and literally build this experiment, you would have a coupling efficiency or collection efficiency of 10%. So every time that the atom emits a photon, and kind of releases some information or quantum information, you only get it 10% of the time, and 90% of the time, it's lost. So that's not a kind of old problem, and there's kind of also well-established solutions. So one is simply just to use many atoms instead of one. And there's kind of well-known notion in quantum optics that you can have collective enhancement. So particularly if I had n atoms, but just sharing one excitation, if that excitation is in a superposition, so atom J is excited with some relative phase e to the ik rj, then it's known that the system can, can basically efficiently emit into a direction dictated by this k vector itself. Okay, so this rate of emission into this kind of preferred direction can actually scale with the number of atoms, while the emission into 4 pi is still kind of independent. So excited atom emits into 4 pi at the same rate that a single isolated atom would. And now the branching ratio of kind of what's the likelihood that you collect information versus you lose it. Now you get this kind of factor of n, the number of atoms, enhancement. And this kind of parameter here is known as the optical depth of your atomic ensemble. And if you treat the branching ratio as a kind of likelihood that you collect quantum information versus lose it, it kind of makes sense that this optical depth sets a fundamental limit to the error of basically any application that you would want to carry out.
You take the atoms not in an ordered fashion, but they are
so far no.
randomly.
Yeah, so at least in the at least in the standard textbook description, your Maxwell-Bloch equations, the positions don't matter.
Okay.
So we can ask whether that's correct or not, but in the textbooks, the positions don't matter at all.
Yeah.
Okay, so this idea that optical depth sets a fundamental limit, you can just find examples of that in millions of papers. Here's a review of modern physics about light and atomic ensembles. And at the beginning, they say having a large optical depth is the most significant requirement for anything you want to do. Here's a kind of more specific example. So if we go to quantum memory or photon storage, it turns out experimentally there's actually a lot of different protocols that you might try to implement to do a quantum memory. So a quantum memory is just that you have maybe a photon qubit and you try to map that in a reversible fashion to a collective atomic excitation, hopefully to make it live longer. And there's this really nice kind of theoretical analysis which said that in the lab you can take any protocol you want, but if you really optimize it, you're going to get the same maximum efficiency in the end, which only depends on the optical depth of the medium. And what they found asymptotically is that error goes like kind of 5.8 divided by optical depth. So to give you a sense of what that looks like practically in a lab, here's some experimental data from a state-of-the-art experiment where they do quantum memories for photon qubits. And what they're plotting here is the efficiency, or 1 minus the error, as a function of optical depth. Okay? So one thing that you see is, as you first increase the number of atoms or crank up the optical depth, the efficiency gets better. It tends to grow pretty slowly as a function of optical depth. And it's not like the number of atoms in the universe is really limited resource, so you can just crank up the atoms more and more. But then what you see is that the experiment doesn't get better anymore. Eventually, when you put in too many atoms, the error actually starts to increase again. And basically, the reason behind that is simply that these are kind of just fundamental limits. But actually, when you have a huge number of atoms, it's very hard to kind of use it in a fully, it's not kind of fully useful in some sense. So other technical problems pop up when you're trying to work with huge optical depths. And we could just kind of take as an empirical fact that having too much optical depth makes your experimental life hard. Okay, so this is a kind of this is just one particular experiment, but I would say this kind of trend is pretty typical for many of the things that you would like to do with atomic ensembles. So here you see that you get stuck with an error of 30%. Okay, so it's not big, but it's not very small either. And then the question is, if that's the kind of general state of the art for experiments, can we find a kind of new way to reduce the errors even further? So to talk about how we might find a new way forward, maybe we should just take a step back and ask, what's the underlying theory that we use to arrive at all these kind of physical conclusions in the first place? So you might ask, well, atoms and light sounds pretty fundamental, so is it a full microscopic quantum theory? But then if you just try to count the number of degrees of freedom you need to construct such a theory, it looks pretty daunting, right? So a typical atomic ensemble can easily have 10,000 atoms. If they're two-level systems, which is the minimal model you need to couple to the light, now you're talking about a Hilbert space of 2 to the 10,000. I haven't told you where the atomic positions are. Likely, if you're experimentalist, you don't know where they are, and they're actually kind of fluctuating as a function of time. And then we have the photons. So if we're in free space, that's an infinite dimensional Hilbert space, because you can have any photon number, direction, frequency, et cetera. Okay, so when you look at that, obviously, that's not where the constructed theory comes from. Okay, so this is a kind of microscopic approach. And what essentially quantum optics does is it takes a very close analogy to what we do in classical optics. So this prism, if you think about it microscopically, is actually pretty complicated. There's 10 to the 23rd degrees of freedom. But when you open up an optics textbook, it doesn't say, let's understand this prism by diagonalizing this 10 to the 23rd sized matrix, right? So what makes this problem simple is that we say in optics, optics basically depends on the fact that you can come up with a macroscopic description of such a system, where all the optical properties are purely described by one single number, the refractive index, along with the shape of the system. So once you know those two things, you can then easily understand how this prism works. And so the most kind of conventional approach to atom-light interactions is to kind of do an analogous thing. So you intrinsically have a collection of granular objects, atoms, but then you say, well, I'm just going to smooth that over into a smooth medium. And in the case of quantum optics, what it means is it's essentially a kind of smooth bosonic quantum field. Okay, so that's where the kind of conventional theory of atom-light interactions is based. And it's clear what's missing is the granularity of the system. But then you might ask, what's the main physical consequence? What are you throwing out fundamentally when you smooth out the granularity? And one important thing that you miss is you miss the concept of multiple scattering of light off of granular objects, and also the associated wave interference coming with that. And obviously, these kind of smooth theories worked very well historically in quantum optics. But these days, when it becomes easier and easier to generate dense quantum atomic media, so when the distance between atoms becomes smaller than a wavelength, and maybe they can even become ordered and so on, You might expect that that kind of multiple scattering now becomes a, could potentially become a very kind of non-perturbative problem. And so one of the consequences in terms of how well you can carry out applications is that, so if you believe that, so if I convince you that the emission of light into the far field, into 4 pi, fundamentally should have interference built in, then from the standpoint of atoms, it's really kind of inconsistent with saying that atoms emit light or coupled to independent baths, right? So the emission of excited atoms should fundamentally be a correlated effect, and it's that correlated dissipation that encodes wave interference into the problem. So that's the kind of general idea, and to give a sense of why that might be useful for applications. If everything just simply depends on the branching ratio of the likelihood that you collect light versus you lose it, so maybe by kind of playing with the emission into 4 pi and using interference, you can not only get the kind of usual collective enhancement of emission into a good direction, but maybe you can use destructive interference to shut off the emission into 4 pi. And if you're lucky, maybe that emission into 4 pi will even depend on atom number. So the more atoms you add, the more you can suppress that emission. And one of the punchlines of what I'll discuss in the coming slides is that that suppression can actually, in some cases, be exponential in n. So now when you compare it to the standard optical depth prediction, you can win exponentially. OK, so that was a kind of extended introduction and motivation. And from there, I guess you can kind of identify 3 general big questions to ask. So one is how do you come up with a theoretical framework, hopefully a tractable one, which includes granularity and wave interference into light-matter interactions. And then if you go through that trouble, does it actually have interesting consequences? So can you actually carry out applications with better error bounds compared to what the textbooks say? And then, aside from applications, if you have a theory that you might consider more fundamental, does that new theory give rise to new quantum phenomena that you would not be able to predict from previous theories? Or maybe just better understanding of phenomena that were kind of previously elusive to understand in the past. OK, so how might we construct such a theory? So again, this kind of full microscopic quantum theory seems out of bounds. But if you accept that we want to include granularity, then it's kind of hard to get rid of this part of the Hilbert space. So then, as strange as it sounds, the only thing you can reasonably conclude is the way to kind of talk about atom-light interactions and include wave interference is to get rid of the photons somehow. OK, so that sounds kind of strange, but let me kind of show that it's possible and it's maybe kind of a natural thing to do. So to be a little bit more specific, what's the general problem that we want to study? We have a collection of atoms. Maybe we know the positions. Maybe we don't. We shine in an input field, which we presume that we know. That will start to excite atoms, and the atoms will start to emit photons. Those photons can then be multiply scattered, so re-emitted and absorbed multiple times. And then what we would like to do is be able to calculate the arbitrary correlation functions of the total field coming out in space and in time. And just to kind of be a little bit more specific for the purposes of this talk, when I say atom, I'll take this kind of minimal 2-level system with an excited state and ground state, which is coupled to light. So this transition has some well-defined resonance frequency omega Eg and some associated wavelength lambda Eg. And then if you just have a single atom up in the excited state, there's a well-defined spontaneous emission rate, gamma naught. So my claim is that it's actually formally easy to write down what the total field is. So you can always write, just as in classical optics, you can always write the total field as the coherent sum of what you send in, plus the light which is rescattered by the atoms. And in a kind of Heisenberg equation language, the field that's rescattered by the atoms depends on the quantum dipole moment, which is just the kind of lowering operator, sigma minus, for atom I, times some electromagnetic Green's function, which describes how a photon originating from atom Ri propagates out to your detection point. And again, that Green's function in free space is nothing more, encodes nothing more than the kind of well-known dipole lobe radiation pattern. OK, so this is kind of elegant equation because what it indeed says is that you don't really have to treat the light on an equal footing. OK, so the only hard part of the problem, so if you know what you send in, the only hard part of the problem are the real degrees of freedom are the atoms, which are then taking those photons and rescattering them and maybe adding quantum correlations and so on. OK, so then we have to figure out what are the atoms doing. So the atoms at some abstract level will be driven by the total field. But then I just said the total field you can go and express in terms of other atoms. So then the resulting equations of motion for the atoms can be described by some kind of reduced density matrix. And so the interactions, on one hand, have a kind of coherent part, which is now in the kind of spin model language, looks like kind of a sigma plus, sigma minus. And that kind of makes sense. What it says is that one atom which is excited can go down to the ground state, emit a photon, and that photon can be absorbed by another atom, and that atom will go from the ground state up to the excited state. And the amplitude of that interaction will depend on the Green's function, which just describes how a photon propagates. Oh, OK, yeah. So I didn't mention that explicitly, but the big cheat for atoms, which makes which allows for the simplicity, is that's a very good approximation for atoms. And roughly the reason why is that the atoms, they tend to be very high Q objects, so they're very narrow line widths. So anytime you shine in near resonant light, you get a ton of dispersion and delay. And that delay completely dominates the delay that you would get from just free space propagation. Oh, yeah. So there's a self term that you have to, of course, get rid of. But then, yeah, so you don't have to, I would say that, so Clausius-Mossadi, of course, is like an approximation, right, of the field seen by one atom from neighboring atoms. So we don't explicitly try to put Clausius-Mossadi in there, but it should be implicit, that if you do this calculation properly, that you'll see Clausius-Mossadi emerge in some sense, if the Clausius-Mossadi. Yes, yeah, so yeah, exactly. Right. OK, so you get coherent interactions between atoms, but you also get dissipation, because again, an excited atom could just emit a photon out to infinity. But the point is that in this kind of master equation that describes the dissipation, you now have a sum over atomic pairs, which is basically saying that you have correlated dissipation rather than independent. And it's that correlated dissipation that encodes wave interference effects. So going forward, so of course, the full system is described by this master equation. But going forward, what you can do is you can take this kind of coherent Hamiltonian and just split off this part of the master equation of dissipation, combine those two, and create some kind of non-Hermitian Hamiltonian that partly describes the coherent interactions and loss. Okay, so again, you can try to diagonalize this Hamiltonian and so on. It doesn't give you complete information, because it doesn't tell you about the kind of jump terms in your master equation. But it turns out that doing that actually gives you a lot of good intuition of what the overall physics is. OK, so to see some of the consequences, we can consider a relatively simple problem. Let's just take a 1D chain of atoms, so an array with some well-defined lattice constant d. And of course, the full spin model can be really complicated, but we can simplify our lives and just look at maybe a single excitation. And in that case, if I have an infinite system, I know that the eigenstates of this kind of effective Hamiltonian are going to be block modes. Okay, so it's a superposition of atom J being excited with some phase e to the ikz. And then because this Hamiltonian is non-Hermitian, I'll have a complex eigenenergy where the imaginary part describes dissipation. So this is just the kind of atomic part. When I have an excited atom, that atom will try to start radiating. And so this state here will start to generate an associated field, which also has to obey Bloch's theorem. So in particular, if I take a kind of plane wave decomposition, the z component of this electric field is also going to look like e to the I kz. And so life becomes interesting if you consider taking a sufficiently small lattice constant. So if you take the lattice constant to be smaller and smaller, the size of your Brillouin zone gets bigger and bigger, and the maximum allowed Bloch vector increases. And at some point, the magnitude of this Bloch wave vector is going to exceed the dispersion relation of light, omega over c. And so once that happens, what it means is that this kind of electric field or electromagnetic field that you generate is no longer a radiation wave, it's evanescent. So it actually can't carry away energy. And so once that happens, you can then automatically conclude that the decay rate of those particular block modes will be exactly 0. So I have an excited atom, but it's never able to shed off that excitation. And that's very different from what the Maxwell block equations say, which is that once you have an excited atom, it's going to emit at a rate into 4 pi that you can never control. So if you're a little bit familiar with optical fiber physics, what I basically told you is just it's the same mechanism. So this kind of chain of atoms is like a fancy optical fiber. So instead of talking about infinite chains, you can also talk about finite size systems. And then you can ask, what's the most subradiant or what's the most long-lived eigenstate of a finite size system? And it turns out the smallest decay rate goes like 1 over number of atoms cubed with some integer index alpha squared, which just kind of indexes the subradiant states. And the fact that they're kind of in a finite size chain, the fact that the decay rate is small but non-zero is again exactly analogous to fiber physics. So some of you might have these kind of optical fiber lamps. And so you know that if you have optical fiber, it guides light perfectly. It doesn't shed radiation into 4 pi, except when you cut the ends, right? So when the light reaches the end of the fiber, then that light can really spray off into free space. And that's where this kind of dissipation is physically originating from. OK, so without going into details, if you can really have excited atoms that can not emit into 4 pi, it's not hard to imagine qualitatively that that can lead to improved protocols for quantum information tasks. So for example, if you analyze a quantum memory, you can show that the kind of error in the quantum memory as a function of atom number can be exponentially better. Yes.
The reason why it does not predict is the same reason why it's hard to get it exactly.
OK, you're right.
Okay,
yeah, so that part I haven't told you at all. Right, so the challenge then is how do you couple, so you have a photon, you want to use your atoms as a quantum, you want to use these long-lived modes as a quantum memory. And so I didn't tell you how you couple into those states, but it is possible to do. My plan was no, but I can if you want. Well, OK, so to get this, what we do is, right, so if you accept that these long-lived modes are basically like some fancy optical fiber, then you can take one way to couple to these evanescent modes is through another evanescent mode. So now if you say I have some nanophotonic interface nearby, like an optical nanofiber, photonic crystal waveguide, then those guided modes can couple to these special states perfectly fine, but they can't emit into 4 pi. OK, so you can get exponential improvement in quantum memory, polynomial improvement in photon-photon gates. My personal hypothesis is that you can find a big error improvement for basically every application you want to do. So why do I say it's a hypothesis, and why am I not proving it? Well, most of the other things that you would like to do are many bodies. So you have many atoms, but you send in many photons at the same time. And that's where this kind of spin model really becomes challenging. You're trying to solve some out of equilibrium, long-range dissipative spin model. So I'll be the first one to say that we don't know much about this regime, but we know a little bit. And so maybe in the kind of couple minutes that I have left, I might just try to kind of throw out a little bit of what we do know and just try to pose some interesting questions. So one thing that we can do is we can just take the same 1D chain and excite the system very heavily. Okay, so maybe just completely invert the system. And at least numerically, we can look at what's the excited state population as a function of time. And as we increase the atom number, and if we replot the excitation number versus time on a logarithmic scale, we see at long times the decay of population isn't even exponential anymore, but has a kind of power law, slow power law decay. Okay, so we can just treat that as a kind of numerical observation or fact. Also, what's kind of interesting is, again, if you take that same system, you globally excite it, what you can look at is, so you can take different snapshots in time. So if you wait long enough, of course, you have less excitations than you started with. But then you can also look at the kind of position correlations of where those excitations sit. And it turns out as you wait longer and longer, it appears apparently that there's some kind of Pauli exclusion or fermionic principle appearing. So once you know where one excitation is, the next excitation is kind of smoothly repelled away. Okay, so you start to develop spatial correlations. I guess I don't have time to really get into the details. But what you can do is you can kind of check that. So basically what we're trying to do now is we're trying to understand subradiance beyond one excitation. And it turns out that numerically, taking kind of fermionic ansatz works pretty well. So in other words, if I give you the set of single excitation subradiant states, multi-excitation subradiant states can be constructed more or less from a kind of fermionic or Slater determinant of single particle states. And so that's a kind of interesting statement that now subradiance looks a little bit like the many-body physics of nearly free fermions. Okay, so with that, I'm basically done. So I guess what I was trying to do at the end is just basically in the end, we don't know a lot about the many-body regime, and I guess I'd love to get your feedback. But we know a little bit. So in terms of what we know we can do, we know this kind of spin model is good for kind of developing new numerical techniques to study many-body states of light. It might help to answer questions even beyond quantum optics, like why is refractive index of materials so small? Just kind of to throw out some open questions, we know that MPS works very well for this spin model in 1D. But why does it work? So if it's a long-range system with long-range dissipation, you might expect MPS to blow up in your face, but apparently it doesn't. Just to get a handle on this spin problem, you might consider, what if I have disorder? Is it possible that these atoms and photons could enter in an MBL phase? And does that provide some way to understand this spin model in some regimes? If you have 2D arrays, is it possible to come up with topological order in the systems? Is that a concept that even makes sense? In the many-body regime, why do we get free fermions? So it's kind of interesting, but why don't we get something more exciting? So those are just some kind of, to give a flavor of questions that we have at the moment, and thanks for your time.